Hello, everyone. We are continuing to power through Chapter 6 here. This is Part 3 of the Chapter 6 notes, and it will be dealing with power. I refer you to page 8 of your note packet, and that's where we're going to be picking things up when we're dealing with power. So when Darth Sidious / Emperor Palpatine is talking about unlimited power, what exactly is he referring to? Well, power is defined as the time rate at which work is done by a force. So in other words, it's how quickly some amount of work can be done by the force in question. So the average power is defined as power average equals delta W over delta T, which is sometimes written as W over T, where capital W equals work during a given time interval, and lowercase t is that time interval length in seconds. So the reason that you normally see delta W as opposed to just plain W is that the units of power are in watts, and the abbreviation for a watt is a big capital W. So it's sometimes written this way, again, to disambiguate things, and so it's a little bit more clear. The instantaneous power, or the instantaneous rate of doing work, as you might imagine, is the limit of this function as t goes to 0. And once again, your calculus nerves should be crackling here, because that's just simply the derivative of the work function with respect to time. The SI unit of power is the watt, which is abbreviated with a big capital W. In the British system, the unit of power is actually the foot-pound per second. And the reason that this conversion is still there is that in the United States, we actually see in engineering foot-pounds still being used. I also kind of don't mind this as much, considering that the initial studies on work and on power were being done by James Watt and other Englishmen, and these were the units that they used. And the SI, the Système International des Units, didn't come until about 40 years later after this research was done. So 1 watt is equivalent to 0.738 foot-pounds per second. Another unit of power is the horsepower, which is 550 foot-pounds per second, or equivalent to 746 watts. Now, that's kind of a weird unit when you think about it. I mean, especially in the metric system, where we're not used to seeing increments of 746. However, this is the result of empirical experiments where James Watt harnessed a horse to one end, and he tied a weight to the other, and he simply saw how fast that horse could move that particular weight a particular distance. And he found that the average horse was producing 746 watts of power. So I don't know if there are, better or worse horses out there, but for better or worse, this is what we call a horsepower. So how exactly do I get from 1 watt to 0.738 foot-pounds per second? Since 1 foot is equal to 0.3048 meters, and 1 pound is equal to 4.448 newtons, if I take a foot-pound per second and I plug in the foot in terms of meters, and I plug in pounds in terms of newtons, I find that 1 foot-pound per second is equal to 1.3558 joules per second. And if you divide both sides through by 1.3558, you find that 1 joule per second is equal to 0.738 foot-pounds per second. Now, just a friendly reminder, if you do any further work in this world, make sure to keep your units straight. This is the Mars Climate Orbiter. It was launched in 1998, and it crashed into the surface of Mars, which is not the point of an orbiter. The reason for that crash, and the reason that this $125 million mission was lost, is that there was confusion between newtons and pounds. The Jet Propulsion Laboratory, which designed the mission, assumed that the contractors that were building the mission at Lockheed Martin were going to make the conversion between newtons and pounds automatically. The contractors didn't do so, and so you had basically a rocket that was producing a lot less thrust than it was supposed to, or it was programmed to produce less thrust than it actually needed to, and we lost the orbiter. So make sure that, again, when you're dealing with English units, and you might, if you actually get into engineering, make sure to keep the English units and the SI units straight. In this course, I think we're going to be dealing exclusively with SI units, but this is a lesson for real life, right? So let's take a look at a couple of power problems. Let's say that your job is to lift 30 kilograms, 30 kilogram crates, a distance of 0.90 meters. So while your muscles may have a lot of power, unfortunately you don't have a lot of political power, and you're busy hefting, about 55 pounds, about a yard straight up all day, which is not a lot of fun. Let's say, how many crates would you have to load onto the truck in 1 minute for the average power output you use to lift the crates to be equal to 0.5 horsepower? First thing we want to do is we say, all right, power, or average power, is equal to delta W over T, and we know that work is equal to the force times the displacement, or the distance that we have to lift to this. How much force do we need to exert to move this 30 kilogram crate any distance at all, actually, in order to accelerate it in the upwards direction? We have to overcome the force of gravity, and that means that F equals ma equals 30 kilograms worth of mass times the acceleration due to gravity, or 294 newtons. The amount of work that we have to do to move one crate is that force, or 294 newtons, times the distance we are moving the crate, which is 0.9 meters, or 264.6 joules needed to move one crate. So the question we're asking ourselves with this power is, assuming that I have an average horsepower of 0.5 horsepower, how much power is that? That's 0.5 times the definition of horsepower, or 373 watts. And again, this big W is the reason why we use delta W rather than just plain old W, so we don't get the W's confused. We can then say, all right, given this amount of power, how much work can be done in 60 seconds? So the work total over 60 seconds is 373 watts. So the total amount of work that we can do in that 60-second period is 22,380 joules. You just, cross multiply here. We know that you're generating 22,380 joules in that 60 seconds, and that you need to use, or you need to generate 264.6 joules for every single crate that you are lifting. So you go ahead and divide 22,360 over 264.6, and we find that if you have an average power output of 0.5 horsepower, you can lift 84.6 crates in 1 minute, and we're going to round that down. We say it's going to be 84 crates because I've never heard of anyone lifting 6/10 of a crate up onto the wagon. I suppose you could say that you're lifting it 6/10 of the way, but in a case like this, when you're dealing with discrete units, it's best to round down. Say there's an average power output of 100 watts. We kind of do the same thing. We say, how much work are we generating in 60 seconds? We find that to be 6,000 joules. Each crate still requires 264.6 joules of work to move. We say 6,000 joules over 246.6 joules per crate. That comes out to be 22.68 crates, or 22 crates. Okay. Last question is, how many joules of energy does a 100-watt bulb use in 1 hour? We have 100 watts, and we have 3,600 seconds in an hour. We have 60 times 60 seconds in a minute, 60 minutes in an hour, 3,600 seconds in 1 hour. We find that the work required, or the work that is generated, rather, in the 3,600 seconds is 360,000 joules, which we can also call 360 kilojoules. And that is our answer. So finally, we have this last example problem. At a certain instant, a particle-like object is acted on by a force F equals 4.4 newtons times I cap minus 1.5 newtons times J cap plus 7.0 newtons times K cap, while the object's velocity is V equals negative 2.9 meters per second I cap plus 4.4 meters per second K cap. What is the instantaneous rate at which the force does work on the object? So if it's asking you for the instantaneous rate at which force does work, it is asking you for the instantaneous power. So we're trying to solve the instantaneous power in this particular example. We know what the work is going to look like, what the work scalar is going to look like. That is the dot product of the force vector and the displacement vector. Now, the force vector is already with us, but what is the displacement vector? Well, as you well remember, the displacement vector is going to be the integral of the velocity vector with respect to time. And we go ahead and do that. We have this velocity vector. We integrate it, and we find that the position vector is now negative 2.9 t times I cap plus 4.4 t times K cap plus c. Don't forget the c. A lot of people have been forgetting the c. In this case, the constant is actually going to be 0. We're not told otherwise. We're not told that this is already moving a particular distance, before we even factor velocity into it. But you have to consciously remember to scratch out that c. That's a very important step. That's something I've seen. A very common mistake on quizzes, for instance, is not including the c. All right? So what work is going to be is this force vector dotted with this position vector. Again, we're just taking the constants in front of I, J, and K cap. We go ahead and execute that dot product, and we find that the work is going to be negative 12.76 t plus 30.8 t, or 18.0 t. That's the dot product of work. So instantaneous rate at which the force does work, that's going to be the instantaneous power, which, as you will recall, is the derivative of work with respect to time. And that means that the instant power is the derivative of this guy. So we go ahead and we plug that in there, and we find that the instant power is equal to 18.0 watts. All right, so that concludes part 3. We're going to move on to part 4, where spring is in the air. So stay tuned, and thank you for watching.